we know what molecules are, so let's get into chapter 6 where we are describing how to draw them in a reasonable way. So the goal here is to come up with representations of what these molecules look like so that we can look at those representations soon and use them to explain the behavior of the molecule, right? So we're not just drawing these things on paper for no reason. We need to be able to draw on paper a representation to see that if we want to be able to explain why water is a liquid at room temperature, why salts will dissolve in water but oil will not. Okay, so there's lots of properties, the density, the viscosity of water, the boiling point of water. Properties for not just water, but a variety of substances can usually be explained if we can understand how the substance looks, and we can say something about how the electrons are behaving in that substance. So that's what we're going to do moving forward. So to represent the structure, we want to talk about molecules that actually exist. We have to be able to draw structures for relatively stable substances that actually exist. So the main driving force that will allow us to come up with stable, reasonable structures is the octet rule. And when I say octet rule, what I mean is noble gas configuration. Right? So when these atoms come together, they have a tendency to make the same number of electrons as a noble gas. And if it's a molecule, they will do that by sharing electrons with other atoms. So, simple example, we already saw with hydrogen. Fluorine does a very similar thing to hydrogen, right? Fluorine has 7 valence electrons. We got 7 dots. It needs 1 more. Well, so does this fluorine. So if they just come together, the 2 that they have that were unpaired can now share between them, and they'll both have 8. Right? So this fluorine has 8, including the extra one it got from the other one to share with it. And this one has 8. So when it comes to the octet rule, shared electrons count toward both atoms' octets. So usually instead of showing a couple dots between them, we show a line. I think it maybe just looks a little bit cleaner. But remember, it's not a line between them. It's not like a rope, or something holding them together. This line is really a pair of electrons in an orbital that's extending over both atoms. And within that orbital now, the electrons spend most of their electron density in the middle of those 2 atoms to attract the 2 nuclei together. And then the pairs that are not shared are called lone pairs, and that's a term that's pretty much universally used. So we'll start calling those pairs that are not shared lone pairs. So we have covalent bonds, and we have lone pairs. So when I draw a Lewis structure, I usually show the shared electrons as dashes or lines, and the lone pairs as individual dots. So for water, you could show it like that. It's helpful to show them all as dots initially because that helps me to make sure, when I'm drawing a structure, to make sure it's reasonable, I want to count to make sure there's actually 8 electrons around all my oxygens, nitrogens, and carbons, all my group 2 atoms that are not exceptions, and I want to make sure each hydrogen has 2 electrons around it. And then if I want, I can convert that into the way we would normally see water, which is with lines for the covalent bonds instead of pairs of electrons. So that's, so far, nothing unreasonable or outrageous. But we want to make sure we got this basic stuff down so we can build on it. So 6.4 says, explain the octet rule and why it applies mainly to second period elements. We were talking that before when Marcus asked about exceptions. So in the second column, boron is an exception because it can't pick up enough electrons to make neon, creates too much of a charge imbalance. But the octet rule applies, octet rule meaning 8, applies to carbon, nitrogen, oxygen, and fluorine. So really it's 4 elements, 3 of them are really common, so that's why it's such an important and helpful rule. 4 elements that we really will never have more than 8 electrons associated with. But as we said before, the third column or third row on the periodic table and below can have more than 8. And that's because in the third energy level there's space for more than 8 electrons. In the second energy level there isn't space for more than 8 electrons. Maximum of 8 electrons in the second energy level. So the octet rule applies more steadfastly to elements that have their valence electrons in the second energy level. That's the point of that question there. So then if we just look at 6.8 real quick, just a little bit more about covalent versus ionic. In part A there they give us 2 atoms and they say if these 2 atoms were to form a bond, would it be more likely to be a covalent bond or an ionic bond? Okay, so when you're looking at this question, covalent versus ionic, the first thing you want to ask yourself is, do I have 2 nonmetals or do I have a metal and a nonmetal? If I have 2 nonmetals, there are a few exceptions, but almost every time it will be covalent. Right? Because what do nonmetals need? The nonmetals are on the right-hand side near the top. What they need, because they're close to a noble gas, is to pick up additional electrons to make a noble gas. So I could make both atoms do that to pick up the electrons they need to make a noble gas, but then they would have a negative charge. The nonmetals can form ionic compounds, but they can't really form ionic compounds with other nonmetals because when the nonmetals form ions, they form anions, negatively charged ions. And so 2 negatively charged particles would never come together and form an ionic bond, right? To make an ionic bond, I need a positive and a negative. That's why I usually need a metal and a nonmetal, because it's the metals that form the positive charges. They're the ones that have loosely held outer electrons. The electrons fall out. They have a positive charge, and then that attracts them to the nonmetals that have a negative. So I'm not going to have a bond between these. If I want to make a bond between nonmetals, I don't want them usually to be charged. I would want them to be neutral, in which case they would both have 7 valence electrons. And so then I can see, okay, these 2 in the middle, they need to be shared. And so I know that that is going to form a molecule or a covalent compound rather than an ionic compound. If I look at part B, I can see the opposite. Here I've got magnesium and fluorine. So fluorine can have its 7 valence electrons. It can pick up an additional one and share it. It can form a covalent compound, but not with magnesium, because if magnesium were to share its electrons with fluorine, the magnesium wouldn't make a noble gas configuration. Right? If magnesium, which has 2 valence electrons, keeps those and shares them with something, it still has them associated with it. It can't make a noble gas configuration. Especially the metals in group 1A and 2A. They must lose their electrons and become positive to make a noble gas configuration. They cannot make a noble gas configuration by sharing. They're not going to form this covalent bond here. The magnesium needs to lose its 2 electrons completely to make the same number as a noble gas. So I can predict that the magnesium will end up with a +2 charge, and the fluorine thus must have a -1 charge to make a noble gas configuration. So I will need 2 of those to balance the overall charge when I have my formula MgF2 for that ionic compound rather than covalent compound. So you should be able to, now at this point, we have some more background. If I give you some elements and ask you to predict the most likely type of bond that would form between them, you should be able to do that. Alright, so there's a couple types of bonds. There's single bonds, double bonds, and triple bonds. And we're going to talk about them now, and then later when we talk about the step-by-step procedure to draw a Lewis structure, we'll talk about how to figure out when they need to be employed. Single bonds are a single pair of electrons shared between 2 atoms. So the single bonds in water has a single bond. Why? Because the hydrogen needs 2 valence electrons. I wouldn't put a double bond in here. It doesn't need 4 valence electrons. It needs 2 to make its noble gas configuration. Double bonds are formed in situations where an atom maybe doesn't get enough electrons around it if I made a single bond. So I'm thinking about CO2 as a molecule, 1 carbon and 2 oxygens. I can't have single bonds here because then the carbon only has 2, 4. It only has 4 electrons around it. It needs 8 It needs a noble gas configuration to really be stable. So that's why I need 2 pairs there to make the carbon satisfy. Right, so there are lots of examples of double bonds, and there are also a few examples of triple bonds. Right, so for nitrogen, if I think about the nitrogens coming together, when the nitrogens come together, they only have so many valence electrons, right? Each nitrogen brings in 5. And so I only have 10 total. How do I arrange 10 electrons around the nitrogens to allow each to feel like they have 8? I have to share a good deal of them. Right? So I've got 3 shared pairs, so that's 6 total plus 2 more. That's 8 for that nitrogen and 8 for the other nitrogen. So they need to share more electrons. So double bonds or triple bonds form in situations where there aren't enough valence electrons to satisfy all the atoms by making only single bonds. So I need to share extra pairs to satisfy the atom's noble gas configuration. So again, we're using the noble gas configuration to drive how we put the molecules together and how we arrange the electrons in the molecule. And then this just gives you a little bit of information about when you have a double bond or triple bond, how that's different from a single bond in terms of the strength and in terms of the length of the bond. Right, so if we're thinking about a single bond between a carbon and an oxygen versus a double bond, which would take more energy to break up? Right, a bond is an attraction. You've got the nuclei, you've got the shared negatively charged electrons between the positive protons of the nuclei. Those negatively charged electrons are attracting the nuclei in, right? So if I have a single bond which is only 1 pair of electrons to attract the 2 nuclei, that's a strong attraction. It takes a fair amount of energy to break those nuclei apart from those electrons and break that bond. But if I've got more negative charge between the positives, it's going to cause even more attraction. So it's going to be stronger. It's going to take more energy to break a double bond and even more energy to break a single bond. It also makes the bond shorter. Right? So if we look at the length of the bond, the single bond versus the double bond, not a huge difference in picometers, but it's a significant difference. So the more electrons I put between the atoms, the more tightly they pull them close together, because I have more attractive negative particles holding those positive particles closer together with a greater attraction. And so we can see that even more dramatically if we compare the nitrogen-nitrogen single versus double versus triple bond. So that's really relatively straightforward and easy to understand. And then, as we were just saying, each bond, so if I have H2, I know that's a covalent bond now. We know that for hydrogen to be stable, it needs 2 valence electrons. So if I have 2 of those, they have to be sharing. And so there's a certain amount of energy associated with any bond. For the HH bond, it happens to be this quantity of energy. Right? Those are energies that must be absorbed by the molecule. It's very similar to a situation where you're exciting an electron. Right? When we talked about having an electron close to the nucleus, like in the first energy level, you want to excite it to the third energy level. When it's close to the nucleus, it's forming an attraction. If I want to break an attraction, that always occurs by absorbing energy. I needed light or heat or electricity or something to overcome the attraction that electron has in the nucleus and move it to a higher energy level. This is a similar situation. These electrons in this bond are attracted to both nuclei. If I want to break the bond and separate the nuclei, I can't continue to have the electrons attracted to both still. They can only be attracted to one if the nuclei are too far apart. So I have to break some attraction to break that bond. So breaking a bond never releases energy. Very common misconception propagated by certain people who I'm not going to name. Makes my job difficult. Breaking a bond does not ever release energy. Breaking a bond requires an absorbance of energy. Forming a bond releases energy, because forming a bond is a decrease in potential energy. That potential energy is released into the surroundings. Breaking a bond requires an energy to come into the bond to break the attraction that's present there. And we will talk about that in a lot more detail later in the semester. Okay, so another concept that we need to discuss when we're looking at molecules is electronegativity. Electronegativity is similar to electron affinity, just a slight difference, right? When we said electron affinity, we were talking about an individual atom's affinity for, or attraction for, a free electron coming into that atom. Right? The higher electron affinity was the atoms that should make a noble gas configuration by bringing an electron in, or less shielding and more protons to help attract an electron in. Right? So free electron coming into the atom. Electronegativity is very similar, except electronegativity is the attraction an atom has for electrons that it's already sharing with another atom. So not necessarily attracting a free electron in, but attracting electrons it has shared with another atom. So the key thing here is that sharing. So if I have an atom, and that atom is maybe forming a bond, sharing some electrons with another atom, if these two elements are not the same element, then they're not going to have the same amount of shielding. They're not going to have the same amount of protons. They're not going to have the same attraction for the electrons. Maybe both atoms have a noble gas configuration, so that's not really a difference between them. Maybe they're both satisfied and they are both stable. That doesn't really create a difference. But if there's a difference in shielding or a difference in the number of protons, then these shared electrons are not going to be evenly shared. They will be unevenly shared. So if one has a higher electronegativity and it's more electron greedy, it will attract the electrons more effectively toward it. So if we go back to this simulation here, that's what this one here is meant to show. So here I've got electronegativity for atom A and electronegativity for atom B. Electronegativity is the ability to attract shared electrons. So A and B are close enough together and there's electron density between them, holding the electrons between the nuclei. Electronegativity is usually on a scale from 0 to 4, just like your GPA. But there's only one element that's a 4.0, and that's fluorine. Fluorine is the most electronegative element. Why is fluorine so electronegative? Well, when it gets involved in sharing electrons, it has more protons than the other elements in the same row, and it has less shielding than any element below it. So when a fluorine atom has electrons shared, and it has a lot of protons in its nucleus and very little shielding, those electrons are going to get attracted to it. So if I wanted to bond element B, maybe I want to make element B a fluorine. Look what happens to the electrons. They all move almost exclusively to the fluorine. There's a huge difference. On a scale that goes from 0 to 4, that's the whole entire scale. There's a huge difference between 1 and 4. So this is an extreme situation, but it illustrates what happens in a molecule. If you have two electrons shared between two atoms, and the two atoms have different electronegativities, they're going to shift toward the atom with more electronegativity, and they will be more attracted to that atom, and so that atom will have more electron density around it. So that creates a situation then where this atom has a more negative, and this atom is kind of like a positive that doesn't really have much negative around it. It's not really ionic, though, because the electrons are not fully being transferred. So we use a little delta symbol to suggest that it's only a partial quantity of negative charge and a partial quantity of positive charge. So if I made A a little bit more electronegative, then it wouldn't allow the electrons to be pulled away from it quite so much. And if I made it a little bit more electronegative, it would be pulling the electrons. So now it's kind of even, but I can still see that this electron density is more on the right-hand side than the left-hand side, because the right-hand side is still going to have more negative than positive. And we'll see how that polarity, or that opposite charges on opposite ends of the molecule, has a big impact on the properties of molecules when we continue our discussion later. So for now, though, we have now a good idea of what electronegativity is. It's a tendency of an atom to attract shared electrons. And when I have an electronegative atom, a highly electronegative atom in a molecule, it will pull electrons toward it. And so this chart shows them. So what are we seeing here? Same kind of trends we saw before. electronegativity in general increases as we go from left to right and increases as we go from the bottom to the top. And what all the blue ones here are the nonmetals. Those are the atoms that have the higher electronegativities. They have either less shielding or more protons, and they're pulling the electrons in. Right? So when nonmetals share electrons, it's hard for them to form an ionic bond because both atoms have a decent electronegativity and both atoms attract the electrons, so they end up still being shared. When I combine a nonmetal and a metal, something with a very high electronegativity and something with a very low electronegativity, then I have a situation where the nonmetal is so attractive for the electrons, it just pulls them away, it owns them completely. And then I get an ionic bond rather than a covalent bond. So this is just showing another way to represent that trend. That's the same reasons that explain the trend for electron affinity can also be used to explain the trend for electronegativity.